slides today. So in this case, we're going to change to, so it's still external convection, right? But it'll be Bluff objects, okay? So cylinders and spheres, okay? So with the flow over them. So what does that mean? Well, that means now we get a pressure change, okay? And if there's a pressure change, we get a U infinity change. So capital V out here coming to the cylinder in cross flow, okay, is always the same, right? Right here, it's velocity, okay? It's far away from that cylinder, that's the velocity. As we get near the cylinder, okay, this U infinity, like right at the boundary layer, that changes, okay, because of pressure changes. So like right here is our stagnation point. That's where we have zero velocity, right? And our maximum pressure. So we get this pressure change. Where when we were just looking at the flat plate in the section earlier, there's no pressure change here, okay? This pressure here and here and here are all the same. So we didn't have a pressure change that we then changed that, that velocity, that U infinity. Where in this case, in the cylinder and sphere, we do, okay? So we have the zero velocity, the stagnation point, and then the velocity will increase, right, as it goes around, which comes with a pressure decrease. Okay, so increase in U infinity, right, which has a decrease in pressure, okay? And then we hit a point where we get our lowest, sorry, I said the opposite, right? No, wait, increase, yeah, velocity, zeros, increase, yeah, there we go. So then we hit a point where our pressure will now change, same with our velocity, and they'll switch, okay? So now we're gonna have a point where we start increasing pressure. So we increase pressure, okay, and we decrease velocity, right? Okay, so that means there comes a point where there's a minimum pressure point, and then we increase velocity, you know, or increase pressure, decrease velocity as it goes around. And what happens is, we see it here, as in this favorable pressure, where pressure's decreasing, velocity is increasing, we have this nice profile, and then we get this adverse pressure gradient. So now the velocity has to overcome the pressure, right? But the velocity is slowing down, right? And the pressure is increasing. And what actually happens is we get to a point where we have separation, where the momentum can't overcome that pressure increase. Okay, so what starts happening is then you get that flow reversal. Okay, so we then have, you know, our separation point, flow reversal, we get vortices, which change the flow considerably, right? So the flow location of that separation depends upon your boundary layer transition. So on the left, we're seeing a laminar. Okay, in that case, you know, the velocities are lower. Okay, so we get a point, so it's a lower Reynolds number. So we get a point of our separation is here. And that's because the velocities are lower and the velocities or momentum of that fluid can't overcome that pressure change. Okay, so we get separation. Okay? Where turbulent has much higher velocities. So now we don't get separation. So way over here, okay? So now that momentum of that fluid is much higher, much greater, and so separation, it takes longer for that point to occur because it has more momentum. Okay? So in these characteristics, change your friction factor, your drag coefficient, your convection coefficient, right? All right, so if we wanted the drag coefficient and drag force, we can look in figure 7.9, and it'll show a figure that you should also have in your fluids book of looking at flow over a cylinder, cross flow over cylinder, but also it'll show the sphere on it. Okay. All right. So then taking that to heat transfer coefficients, we have figure for the local, right, heat transfer. The local Nusselt number is shown in 7.10. So it shows it over 180 degrees around that cylinder. What that local Nusselt number change is as it goes around that cylinder. Okay, and it shows it for different Reynolds numbers. So if you're at very low flow versus low velocities, laminar versus higher and higher flow versus for that turbulent flow. Okay, and the average Nusselt number. Okay, so that's basically you're integrating the local one or getting a correlation off of those values, and Nusselt number is this. Okay, so then the correlation where Nusselt number is a function of the Reynolds number and Prandtl number, we have equation 7.54 for a circular cross section. We also have for a non-circular cross section. Okay, so cross flow, if you had, say, a square profile, they also have like a hexagon, or they have a vertical plate. Okay, and that correlation they just have in the table these different parameters. Okay, there's also a couple others for the average Nusselt number for a cross flow in a cylinder. There's equation 7.52 and there's equation 7.53, and they have tables of parameters. Okay, there's also a table that goes with each of those. Okay, why do I say that? This one doesn't have that. Okay, that's why you're seeing it 7.54. It's much bigger equation, but it's not changing the parameters that are being used there. So it's more of an all-encompassing one. Okay. And then the other is just making sure you know where the properties are evaluated at. Okay, so this is at the film temperature. So that's TF, which is T surface, it's T infinity divided by 2. Sphere, very similar to a cylinder, and we have our equation right here. Okay. Passing it. Anyways, we have our equation you're seeing on the slides. It's similar to boundary layer development, pressure change similar to flow like a cylinder, and we get our Nusselt number relationship. Okay, all these properties are evaluated at T of infinity, except for the dynamic viscosity is at the surface temperature. Okay, we also see that the drag coefficient is in the same figure as the cylinder's cross flow drag coefficient, which is figure 7.9 if you need it. All right, examples. .53. In an extrusion process, copper wire emerges from the extruder at a velocity VE and is cooled by convection heat transfer to air in cross flow over the wire, as well as by radiation to the surroundings. Part A is by applying conservation energy to a differential control surface of length dx, which either moves with the wire or is stationary, through which the wire passes, derive a differential equation that governs the temperature distribution, T as a function of x, along the wire. In your derivation, the effect of axial conduction along the wire may be neglected. Express your result in terms of velocity, diameter, and properties of the wire. The convection coefficient associated with the cross flow, H bar, and the environmental temperatures T infinity, T surroundings. Part B, now they give us a lot of parameters, and they say neglect radiation, obtain a closed form solution to the foregoing equation for velocity of 0.2 meters per second, diameter 5 millimeters, air velocity of 5 meters per second, T infinity of 25 degrees Celsius, and an initial wire temperature Ti of 600 degrees Celsius. Compute the temperature of the wire at X, where the length is 5 meters, the density, specific heat of the copper, so they give us the density and the specific heat. They also give us the properties of air, the thermal conductivity, and the kinematic viscosity and the Prandtl number, okay? And then part C is now account for the effects of radiation. They give us emissivity is 0.55, temperature surroundings 25, and they say to numerically integrate the differential equation from part A to determine the temperature of the wire at 5 meters and explore the effects of the wire velocity and emissivity on the temperature distribution along the wire. Okay, so in this problem, there's actually only a small section of what we're about to do is new within chapter 7, okay? The rest of it is we're applying concepts that we've already learned before chapter 7, okay? So we see we have an extruder right here, and we're pulling this wire, okay? So this is this wire velocity, right? So we're pulling this wire, okay? We have air basically flowing over it, okay? Cross flow air, okay? The wire comes out with an initial temperature. They want it eventually to solve it have the wire temperature at some distance x, okay? So some distance x, okay? We have surroundings, we have T infinity velocity, we have a length, we have a diameter, okay? We have a wire emissivity. All right, so part A is a differential equation, temperature distribution, T is a function of x, okay? Part B is now for negligible radiation. We're solving that equation at 5 meters. So first we're creating the equation, then we're solving it, okay, at 5 meters. Then part C is more of exploring things because we neglected radiation. They want to figure out what the value is if you include it, and then mess around with some parameters of wire velocity and emissivity. All right, so for the first part, we need to get a differential equation. They told us that we can take it with either the differential surface either moves with the wire or is stationary, okay? So what does that mean? So first, let's say it's stationary, okay? So let's draw our little control volume. This is distance dx. It's stationary, okay? So that means there's wire flowing into it and there's wire flowing out of it, okay? And then we also have convection and radiation off of it, okay? But we have the mass of the wire carrying in energy and the mass of the wire carrying out because it's flowing in and out. So just like mass flow rate from Thermo 1, we apply it there, okay? So this is our first one, okay? So you see it here. Again, that control volume, we have our mass flowing in, mass flowing out. We have convection and radiation, right? All right. So energy flowing in, because we have our mass flow rate. So that's basically this right here is like m dot, density, velocity, area, okay? And then we have our CPT, okay? Like enthalpy. Then exiting, mass flow rate again. And then our CPT, which is T plus dt, okay? And then over that little control volume, we have convection, radiation leaving. And it's steady state because the temperature is not changing because the control volume is staying stationary. So it's always that same temperature of that wire that's flowing through. Okay? So the energy stored inside of it is not changing with time because the control volume is staying stationary. All right, so then if we multiply this out, we'll end up seeing that this cancels, and we'll just have this dt. Okay? So that's what you see here, the negative with the dt. Then putting in Newton's law of cooling, radiation, and our surface area right here. Okay, so now if we put dt over dx together and rearrange, just move things around, we get our equation. Okay, so now we have our equation for temperature as a function of the distance along that wire. Okay, the other way that we could have derived this is if we fix the control volume to the wire. Okay, so if we have the wire right here, and then this is our control volume, the wire is moving, but in this case, so is the control volume. Let me do it this way. Okay, so it's moving at the same velocity. So if that's occurring, that means there's no mass flow rate in or out of that control volume. Okay, because it's moving with the mass. Okay, so that means now though, we still have our heat leaving, so still convection, still radiation in that case. But we have an energy stored term, because now as we're moving along with that wire, we're cooling, right? The wire's cooling as we move along with it. So the temperature's dropping of the wire, so the energy stored is dropping. So we have to keep that term in. So this, for the energy out, convection and radiation, looks just like in the last one. This is our surface area again. Okay, the only thing that's changing is now we have energy stored. This is our volume right here in the parentheses. So density volume specific dt over dt. If we rearrange that, you see we have temperature as a function of time, where this one is temperature as a function of distance, right? So we have distance, which is what we want. This has time. So if we wanted to get this derivation in the form of that, we would need to use velocity to get there, okay? And that's if we basically just divide by velocity, with velocity being dx dt, 1 over velocity is dt dx. So I'm going to use that on each side. dt dx, dt dx. All right, so the dt cancels and we have dt dx. And then on this side, dt over dx does not cancel, so we have basically 1 over velocity, which is what we have right here in this side. So now we've basically put in that 1 over velocity. So we have the same equation we ended up with between whether we kept the control volume stationary or we moved with the wire. We can derive the same equation. Okay, I like this derivation because it's not as many extra steps to it. Okay, so we'll start with that one. Any questions? So that's all part A is asking, is this equation. And actually this equation, this derivation, although a little challenging, it didn't require any new information from chapter 7. This was all just COE on a differential volume, okay? All right, so then part B is where we solve it, all right? So if we take this equation right here and they say, all right, for this part, we're gonna neglect radiation, okay? So now we're just left with dt over dx, and then the convection component right here. While separating variables, we can integrate that equation and get, the solution to it at any distance x, okay? So if we want the temperature at any distance x, okay? So they ask it for its 5 meters, okay, at length L, okay, so they want it, let's go right here, right length L. So we use our equation that we just derived, solve for the temperature at length L. The only thing we see is we have all these properties. We don't have the convection coefficient. So now we're actually doing the new part of chapter 7, and that is all right here. This is chapter 7. And that's getting our convection coefficient. All right, so we have Nusselt number HD over K of the fluid. All right, so that's the equation for Nusselt number. So we need, or for convection, so we're looking for the convection coefficient. We need Nusselt number. We have diameter. We can get thermal conductivity of the fluid. So it means we need an equation for Nusselt number. Okay, so we first get Reynolds number, and then we use our equation for a cross flow cylinder, which we have right here. Okay. And we're just plugging in Reynolds number, Prandtl number, Reynolds number, Prandtl number. And then we plug that Nusselt number, which is 14.4, into our equation right here, and we get 107. So now we have everything to solve this equation, plugs all the values in, put it in our calculator, make some calculator noise like beep, boop, beep, boop, and we get 340 degrees Celsius, okay? So that's part B. Part C is they want you to include radiation. So if you take this value right, this equation right here, and include radiation, the only way to do that is to solve it numerically. So, do a numerical assumption and step through your distance. Okay, so keep this in here and numerically step through it, where you have X and you have T, and you start off with 300, and then you go to 0.1, and then you have, say, 290, and then basically you step through it until you get to 5. And you have 340, or sorry, 309. How did I get higher? Oh, it starts at 600, sorry. Okay, and you get 309 with the numerical integration. Then the last part that they do the parametric study where they change, let's zoom in on this. The extruder velocity, okay, so they're varying the extruder velocity and saying at distance X what that temperature is. And we see right here, the slowest velocity, we get the coolest temperature. With the highest velocity, we get the hottest temperature, right? And then here they're changing emissivity. Here's no, 0, and then here's with 0.8. Okay, so we get a little bit of change, but not as much as velocity, right? Starting off at 600 when it exits the extruder. Okay, so one of the big things you have to do for wire that's extruded is you need to wrap it, right, afterwards when it cools down enough, right? So if we're looking at this problem and you did this analysis and it has to be, below a certain temperature, let's say 200, has to be below 200 degrees Celsius for you to start the wire wrapping in a spool. And this is at your job, at a company that does extruding, would you recommend running the extruder velocity at 0.1 meters per second, or would you do something else? What do you think Like if you're talking to your boss or your boss's boss or your boss's boss's boss, what do you think their main goal in a process like this, in an extruder one, what is their main parameter that they want as high as possible? It's a company that produces wire, right? So what are they trying to do there? Any ideas? Pretty quiet over there. So if you're trying to produce wire, you have a company that's producing wire, right? You're going to want to produce as much wire as quickly as possible, right? So a higher extruder velocity would be the goal, right? So then you're producing more wire, right? So if you want to get the most wire out of it, you want the highest velocity. So the distance, maybe you instead go to make this way longer of a distance that you're having it extrude for outside of it to help with the cooling process for wire before spooling it, versus shorter distance but lower velocity, because you want that production rate to be as high as possible. Or maybe you look at the convection coefficient and try to put velocity of cross flow higher, okay? Because you want, again, production to be higher, not necessarily just changing the parameter that made it work, because the company's goal is production. So maybe you want to go a different route. Okay. Questions? All right, so then there's no questions. We're on to the second half. I know we did the second. We're on to examples then. I know we have one more, sorry. Must have missed this from the other problem class. All right. So in this one, we have a thermocouple. This is 7.65, a spherical thermocouple junction, 1 millimeter in diameters, inserted into a combustion chamber to measure the temperature T infinity of the products of combustion. The hot gases have a velocity of 5 meters per second. Part A is if the thermocouple is at a room temperature, Ti, when it is inserted in the chamber, estimate the time required for the temperature difference, T infinity minus T, to reach 2% of the initial temperature difference. Neglect radiation and conduction through the leads. Properties of thermocouples are, and they give a whole bunch of properties of thermocouples, and then they have combustion gas properties. And part B is that the thermocouple junction has an emissivity of 0.5 and the walls of the chamber are 400 degrees Kelvin. What is the steady state temperature of the thermocouple junction if the combustion gases are at 1000 Kelvin? Conduction through the lead wires may be neglected. And then part C is just playing around with some parameters, parametric study. All right, so we have this thermocouple right here measuring temperature. Okay, it has a diameter to it. We have the walls have a temperature. We have the combustion gases have a velocity in T infinity. And the goal of that junction temperature, that thermocouple, is to measure T infinity, right? That's why you have it inserted into there. Okay. All right, so if we're looking at it, we have this little sphere bead. We're neglecting any losses through those leads. So we have convection coming into it, and we have radiation leaving it, right? Because the hot gases are convecting into that, and radiation is going to the wall, okay, the cool wall. So part A is time to achieve 98% of the maximum temperature from negligible radiation. B is steady state temperature, and then C is that parametric. All right, so A ends up being actually a Biot number, a lump capacitance analysis, okay? So we're using the equation of lump capacitance to get that time, because we're looking at 98%, okay? So 98% of that temperature, okay? and we plug in all the parameters, and in chapter 5, the problems would give you the convection coefficient. So basically now, right here, we're solving that convection coefficient. So we're getting the Nusselt number for the sphere, for the Reynolds number to put into that. Okay, and then if we solve for the Nusselt number, then we can get our convection coefficient, and that's what you see here. And we can plug that into our lumped capacitance analysis, and we see that it takes 6.83 seconds for changes in T infinity here to be seen by the thermocouple there. Okay. Part B is a steady state temperature, so that's just COE of convection and radiation. And in this case, we're setting them equal. We solve, we get 936. And remember, T infinity is 1000. So we're getting some temperature difference between what the thermocouple reads and what the gas temperature is. Here is changing the velocity of the fluid, right, with emissivity. So with an emissivity of 0.5, we're measuring that temperature in the gas. If we're changing the emissivity a bunch of the thermocouple, what is it? Okay, so we get